numbers is an absolute, it's enough to push me along.
That's awesome.
It's so cool.
It's really just one of the more human pursuits, just abstract the hell out of a problem to the point where it's just equations and then bring it back to the real world. It's kind of amazing.
Awesome. I'd probably say cool thing about calculus, like it probably is, it might be one of the most important inventions or most important studies ever done by humans.
I would agree, yeah,
Calculus brought in the modern age.
for sure.
We would have never had anything happen today.
I agree, yeah.
So awesome.
Well, welcome back, folks. Looks like we're ready to get started. We're, for the announcements, in pretty good shape for exam 2. If we take a look at what's going on in exam 2, it's only going up to this section 3.7. So it's going to be pretty much 3.1. We're dealing with our power rules, constant multiple rules, things like that. 3.2 is product rule, quotient rule. Then it was trig functions, chain rule, implicit differentiation. Then we did logarithms, and section 3.7 was just a couple assorted applied problems that we did in the sciences. So that's going to be our extent of our second exam. And the sample exam problems are now posted if you want to take a look at them a little bit early. Well, any questions, folks, so far about the announcements? Okay, well, since we're coming up to a second exam week next week, when it comes to this assignment number 6, when I completely grade this assignment, I'm going to find some way to return it back to you. If you've emailed me your assignment, that'll be easy. If you hand it as a hard copy, then I'll be scanning these graded hard copies and sending it back to your ISU email address over the weekend. That way you'll have an extra opportunity to study these problems here as you're studying for the upcoming exam 2. So take a look at your ISU email address if you turn in a hard copy, and I'll be sending you your feedback. Well, we still have to get through work, so we'll be working on section 3.8, 3.9. The so far due date for assignment number 7 is October 12th, but we're going to do something like we did before ahead of exam 1. Although the official due date is October 12th, our second exam is on the 9th. So if you decided to focus your energy on studying on exam 2, it's not a bad strategy. And I'll accept assignment number 7 on the 16th, so the Monday after. I'll make that official and say an extension here once that gets closer. But essentially, everything we did around exam 1, we're doing it around exam 2, just different assignment numbers and section numbers. Any other questions then, folks, before we get started? Okay, well, with our work today, it's going to start off as kind of a nice light topic, I'd say. An exponential growth and decay. These are topics we've seen before. And so now we're going to take a closer look at it, see how calculus gives us slightly different insight, and extend to Newton's law of cooling. Then in section 3.9, to me, this is a pretty tricky section. We're going to break it down, show how it all goes. It has a lot of commonalities when we're dealing with implicit differentiation. There's chain rules that are hidden there that are really hard to see. But if we can get a really good handle on this section, you can solve some really interesting problems. This one's just a nice problem that could work well for an exam. But we're getting into things like dealing with Boyle's law, what happens with gas pressure. We're also going to be dealing with things along the lines of weird stuff from physics, weird stuff in engineering, and all that kind of stuff. So that'll be our related rate section. Again, it is a tricky section. So anything that you can do to take a look at the information in the book, maybe take a look at some of the examples, it'll help out quite a bit as we start doing our 3.9 in class. Well, that's where we're at so far. And for 3.8, definitely not as bad. Here's how the information starts out. It says in general, so that's always kind of scary. Generality is a wild place. But it says if y of t is the value of a quantity y at time t, think of y as maybe it's a population size. We'll probably use p for population instead of y. If it's money, we might use a for an amount. If it's, say, a mass of something that's disintegrating with a half-life, we might use m for mass. Just think of y as the generic placeholder. So we have, if it's the value of a quantity at time t, and if the rate of change of y with respect to t, right here when they say that much, they're talking about this quantity in Leibniz notation. The rate of change of y with respect to t, that's just a way to say the derivative. If it's proportional to its size, y of t at time t, then we get to write, well, the derivative dy dt equals k times y. Here, k is the proportionality constant that they're mentioning. It's proportional to y of t, so it's k times y indicated down here. So we have an equation, but this equation is different than a lot that you might have seen. We'll call this a differential equation because it's an equation that involves an unknown function, not an unknown number this time. The solution to the differential equation will also be a function. So it's not any different from, say, 2x plus 5 equals 10. The solution to x is a number, but now we're saying the rate of change of y with respect to time is always going to be some constant times y. The solution to that is just going to be any function that satisfies that equation. What any questions so far, folks, with the statements here? Okay, so when we say it's proportional to its size at any time t, it involved this k value right here. Oftentimes it's called the proportionality constant, but in this context, exponential growth of decay, we think of k as the relative growth or decay rate. If it's positive, maybe that's our bank account and the money is growing. We'll say it's the law of growth. If it's negative, we'll say it's the law of decay. Well, that's the setup so far. And because it's not a course on differential equations, it's possibly the first differential equation we looked really hard at. Theorem 2 just supplies the solution immediately. But the more you take calculus, calculus 2 is going to cover differential equations a little bit more. You'll start to get a feel for how these kinds of things go. So it says here, the only solutions to this differential equation, the original one that they showed us, is this class of exponential functions. Y of t equals y naught to the power of e to the kt. Expand that a bit. It involves the growth or decay rate, k, right here. It also involves this quantity. Sometimes people just read this off as y naught. They mean y of 0. And think of y of 0 as the initial size or value or population or amount of mass. I'll just say initial size to start. So that's it so far. We have a differential equation, and what's odd about this is they're telling us immediately the only solutions are these right down here. In a class like, say, college algebra, you'd be focusing a lot on just this, how to work with it, how to build it from given information. But for us, we're going to be using both this right here and this as we solve problems. So the new thing in this section in the calculus class are, now both equations are important. But anytime this one comes up, the equation for the derivative, I'll be sure to make a really big deal out of it and put in a screenshot to say, use this information right here. So that's what we're getting into. That's the theorem already. That's kind of nice. We have a problem right here, and theorem 2 says, here is all of your solutions. But I thought a good way to start this off is, let's see if that's even true. We don't have to take it at face value. It's good to be suspicious, critical. Example 1 says, show that this, y of t equals y at 0 times e to the kt, solves the differential equation dy dt, that one above, equals ky. Let's take another look at the information. A solution to a differential equation is a function that satisfies that original equation. So we're saying this function, where you can put anything in for y of 0, is a solution. Well, what does the solution have to do? We must be able to put it back inside the original equation. Even if it was like, say, 2x plus 5 equals 10, as soon as you find a value for x, you put it back to the original equation and see if you get a true statement out. So what we do immediately for trying to check if that's a solution is differentiate it right here and now and see what we get. Our derivative had better look like this, or else that was a lie. That's not really the solutions. Well, any questions, folks, before we give it a try? Okay, let's try this out then. Really, all we have to do is start with the left-hand side, dy dt. Now our goal is to get here. I'll just circle it for the moment. But we have a function that's supplied for y, so let's make a substitution right away. In place of y is that function there. So you could rewrite your notation. You could put a parenthesis with a prime symbol if you like. I'll keep the Leibniz notation. I write this as the derivative with respect to t for time of this entire thing, y at 0 times e to the power of kt. So that's the derivative we have to take. And it's one of those kinds of derivatives that just makes me feel uncomfortable because there are too many letters inside here. In fact, there's only two numbers, 0 and e, which is about 2.71, but my second number is a letter. That's kind of rude. The best strategy here is we need to determine what's constant and what's varies. First thing is y of 0. It's always the initial population size or initial mass. That's never changing. It's an amount at one instant in time. So we can say here, y of 0 is constant. That helps us out immediately already, because if we're differentiating, we'll use the constant multiple rule right here, since y of 0 is multiplying. Next is that k value. K is also constant. It's the relative growth or decay rate, and that's something that stays fixed in the entire problem. So we'll say here, k is constant. So as we go to differentiate this, we'll have to keep reminding ourselves to use the right differentiation rule relative to when we see a constant and when something varies. So here's our first step. Because y at 0 is constant, we can rewrite this as y at 0, initial population size, times the derivative with respect to t of e to the kt. Because this problem just looks weird with so many different letters, I'm just going to try to go really slow. I'm only going to use one differentiation formula at a time. And that step was the constant multiple rule. Does that make sense to folks to that stage? Awesome, glad to hear that. Now, this derivative isn't too bad. It's like taking the derivative of e to the 5 times x. Well, x is t, and instead of 5, we have a constant k. But there's a larger issue here. When you look at this, would you all agree that's truly a chain rule we're dealing with? Awesome, glad you spotted that. If you're spotting these right away, then I'd say that's a good sign. You're getting a good feel for the chain rule. If it was e to the t, there's no chain rule, and the derivative is done. But if it's e to the kt, we go in this order. Differentiate that first. That's the outer function. And for kt, we'll do that one second. This one is inner. So with that set up, here's our very next step. I'll just go to the right here. I'm running out of vertical space. First, copy in y at 0. Why not? Next, we're going to differentiate right here. The derivative of a base exponential by formula goes itself multiplied by the derivative of its input. And if at this stage you put down just k times e to the kt, I think that's terrific. That's the right step to take. But when they get complicated or just weird like this one, not a bad idea to go back to first principles and do it methodically and carefully. So what I'm plugging in is that whole inner function kt. So it'll go right here and right here. Finally, we have one last derivative to take, folks. Anyone see what the derivative should be right here by the red dot? Sorry, say again. It wouldn't be a 1. It would be a k, good call. Again, think of this. Let's just put a quick analogy. I'll delete this in a moment. But if it was y equals 5t, these are always great analogies to do, even on an exam setting. Make it a little bit more familiar, see how it goes in this familiar setting. And then we'll know how it goes in this setting. Exactly. We're just going to carry that k in when we differentiate. So that's our analogy to help us out. Now let's put it all into practice. Yeah, go ahead. Exactly. It's really the power rule right here. Let's put that 1 in just for emphasize.
Wait, how do you know that k is the constant?
Oh, it always comes from right here. In this differential equation, k is just given as the constant proportionality. But honestly, this was really the only hint right there that it would have been constant. It's kind of one of those things that's implied, but it'd be great if they just say it right out of the gate. Oh, it does? Oh, gotcha. Missed it right there myself. Other questions so far? Okay, so maneuvering through this derivative, it's a weird one, but we get just a K out. So keep an eye on the target. We started on the left-hand side. We're trying to get K times Y. We found our K at least, so that's good so far. So we now have a K. We'll leave it on the far left just to match what we're going for by the red dot. It's now a K times. Now I'll come down here. Let's collect everything else. Y at 0, e to the KT. At this stage, I think we need some good color coding. This Y of 0, e to the KT, we know it by another name. That's Y of t. We can just throw it in there right now. This turns into K times. This looks interesting because it's really a stylistic choice. It could have been said dy dt equals K times Y of t. So you could have put a Y of t here and by the red dot. But often in differential equations, the input is suppressed to the function. And we're just going to write it like this, K times Y. As it's written up here, and that tells us we're done. The moment we differentiated, popped that K out and got K times Y, our punchline, because we have equalities chaining everything together, is therefore the rate of change with respect to time is K times Y, like we expected. Yeah, go ahead. Why was it canceled? Or it was a substitution more. It was more this whole thing, Y of 0 e to the KT. We replaced it with just Y or Y of t. Does that make sense? Gotcha. Other questions or comments so far? Yeah, go ahead.
We basically took the equation, write out a K and called it Y.
Exactly what happened. And that's only reason that this satisfies it. It's just a fluke in how the chain rule works. That if you differentiate this equation in yellow, yeah, your derivative always looks like that. Kind of strange. Other questions at the moment? Yeah.
That taking Y equals Y of 0, that how do you know that was the solution? How did that go? Is that the only one?
It is the only set of solutions. Yes, and the way you would get there, well, you would have to derive it from differential equations, first principles, unfortunately. So it becomes more of a differential equations class at that point.
Okay, so we just take that as given.
Yes, in our class, we're taking this right down here as given. All we were doing in example 1 was, because this is so new, a differential equation, we were just trying to check, how do we even know if we have a solution? The motions are differentiate what you got. And if you can get to this end, K times Y, you know you have a solution. So I'd say that was the major part of example 1, really. Other questions or comments at the moment? Okay, well, we have two things here. We have the differential equation that was supplied. We have the solution that's given. Again, it was given to us. That's kind of weird where it even came from. But now the thing to always worry about is, now that we've differentiated this once, anytime you see a problem that even hints at differentiating your Y function, don't do it. It's already been done. It's supplied here, that's the derivative, and we did again on example 1. So just as a note, since we know dy dt equals ky, we will never be required to calculate y prime. Because if you're given a y in this format, we know immediately that's y prime right here. It's essentially done. That's tricky enough. We'll make, again, a really big deal out of it whenever that comes up in the notes. Yeah, go ahead.
This is going to y of t equals y now times e to the power of t, right?
Correct, yes, absolutely. Other questions so far? Okay, well, let's give this all out a try. So we have a differential equation and its function. We'll turn to those notes the moment we need them. And here's what a typical problem could look like. I'll even pull that up. There's a math button, I guess. So it says in example 2, a bacteria culture grows with a constant relative growth rate. Right here, they actually told us a lot just with that statement. They're telling us that if we write y of t equals the population size of the bacterial culture, then if you're told it's growing at a constant relative growth rate, you can immediately conclude y of t is going to be equal to y at 0 times e to the power of kt. And we have even more, you know the derivative immediately. The derivative of y with respect to time is automatically k times y. So for what's highlighted in yellow, we get all of that information essentially for free. So that's kind of nice. They also tell us bacteria count was 600 after 2 hours, 75,000 after 8 hours. So there's a massive growth rate on this one. And we could put this in function notation. The function, well, I used y of t. I was going to use p of t. Is that okay with the class if we go with a p here? Or should we keep it of a y? Your choice today. Let's go with p. I think that might make more sense. So sorry for the y's there. Let me put these as a p of t. P for population, right? That makes a little bit more sense. If you decide to go into load and call it a y of t, it's completely correct as well. But let's make these just a little bit nicer to look at. Geez, that's a lot of changes. So P of t is the population size of the bacterial culture t hours after the experiment. So we have a P of t here. The derivative is now dP dt equals k times p. So there's our corrections. Now going back to function notation, we can put 600 inside here. And, oh, excuse me, let me try again. The bacteria count was 600 after 2 hours. We put the time inside and we can say population size at 2 hours was 600. Next thing they told us was at the 8-hour time mark, we can write population size at 8 hours. That one was 75,000 bacteria. So I've used all the initial values they gave us, just 2 here. They're asking us, what is the relative growth rate? The relative growth rate is the constant proportionality k. So we're trying to solve for k on part A. So that's pretty much how the problem breaks down. We haven't really gone too far. We've just set our notation and put down most of our formulas. That should have been a P not here in green. Sorry for those. It's always bad to switch functions in the middle of a problem. So now we're going to have to solve for that k right there. Any questions at the moment, folks, with all the setup? Yeah, go ahead. Yes, P at 0. Let me make this look more like a 0. P at 0. My parentheses look kind of funny as well. Okay, so we have 2 equations for just solving for one thing, k. But honestly, there's 2 unknowns. Anytime you write down these kinds of problems, a population size or amount of mass, you want to know the initial value, P at 0. Sadly, they didn't give it to us, right? They gave us a 2-hour mark and an 8-hour mark. And you want to know the growth or decay rate to k. So there's 2 unknowns. We have 2 equations. We should be able to solve this. Let's start with the equation on the left and just see what happens. It says P of 2. Where are you going to put 2? It's going to go right inside here. And that means it also goes inside here for time. So P of 2 equals 600 means I'm going to go here, put in P of 0, e to the power of k times 2 equals 600. So all I've done is I've gone to the left-hand side of the equation and throw the 2 right here. Does it make sense to folks on how that happens? Okay, so if we're happy with this equation, well, still don't know what P of 0 is. We have e to the 2k equals 600. Because P of 0 is on its own pretty important, let's just solve for it and see what happens. We'll get that P of 0 equals 600, divide by e to the power 2 times k. So that finishes off this equation. I'm not getting any farther on this one. But we can redo the steps on our second equation that was provided. P of 8 equals 75,000. Take this 8, plug it in right here, copy that whole side. So we have P of 0, e to the k times 8 equals 75,000. Well, here we're kind of stuck again, right? Except we can make a substitution. Right where there's a P of 0 equals 600 over e to the 2k, we could put it right there. If you do that, there's only one unknown now. It'd be k, the thing we're trying to solve for. So let's make a substitution on our next step. It becomes 600 over e to the power 2k times e to the power of 8k equals 75,000. So the yellow highlighting is going to show where that substitution happened. Does it make sense to folks so far? Okay, now we can combine our bases. E to the 2k divides into the e to the 8k, and we just subtract exponents. So now it's 600. Once I find the pen, let me try again. 600 times e to the power of 6k equals 75,000. This is starting to look like an equation where you can solve for k on, so we're getting close. Next thing you need to do is divide 75,000 by 600. But keep in mind, our exams are open calculator. It can't be a graphing calculator, something like the TI-30XA or X2S. In class, I'll use Desmos again, since it looks about how like a graphing calculator would. Or excuse me, about like how a TI-30XA would look for the calculator portions. Okay, so I'm not worried about the graph. Just imagine this is a basic calculator right here. All I'm going to do is put in 75,000, divide by 600. We have a unique value, or excuse me, an exact value of 125. So now we're done with the calculator. E to the 6k equals 125. Now, at this stage, we're kind of stuck. You can't divide by anything to solve for k. We need an inverse function. Anyone happen to know what it'd be? Exactly. The inverse function is natural log. Apply the natural logarithm to both sides, and you'll be able to solve for k. Here's what it would look like. Natural log of base e to the power 6k equals the natural log of 125. There's always a cancellation with the natural log and the base e exponential, no matter how you compose. So those are gone. You now have the exponent, the thing we wanted. 6k equals natural log 125. Then just divide. I'll put this in blue since this is our relative growth rate. K is now equal to natural log of 125 divided by 6. We could put it in a calculator if we'd like, but honestly, sometimes that's a dangerous step. If you approximate this with a calculator, you should be going between 6 to possibly 10 decimal places because exponential functions are extremely sensitive to rounding errors. If you leave it in its exact form, you'll be at the most accurate you could be, so it's probably the better strategy. But Bob said, what is the relative growth rate? I'll put this in a box to emphasize, there it is. That's our relative growth rate. We never even return to this equation, but we will when we try to find the initial size of the culture. Well, any questions at all, folks, on finding the value for K? Okay, this problem is definitely a little bit tricky because they gave us 600 after 2 hours, 75,000 after 8 hours. If they just gave us the initial population size, it would be a much quicker problem. An initial size is this right here at the moment highlighted in yellow. We need to find that value, but we have kind of all the information we needed, right? We can say the initial size is population size at time 0 When we were solving, we found it was 600 divided by e to the power of 2 times k. And here's k right here. So I'll put that in blue just to emphasize how that went in. It's going to be times natural log 125 over 6. And you could reduce that, but honestly, we're just going to throw this into the calculator, get a numerical figure for here. So no harm if you leave it just as it sits. Let's throw this back in the calculator and see what we get. So 600 divided by e to the power 2 times natural log 125 divided by 6. Finally, we have an exact value of 120 for all of that stuff there. So we get 120. But by the way, if you have your calculator with you today and you're trying along with the class, let me know if you're getting different values, since, I mean, it's good to practice with this as well. Anyone have any questions on getting that calculated through the calculator? Okay, if you ever do, I do have a calculator I can use. I mean, Desmos is nice, but it formats it too much for us, right? So this is kind of awkward because we're not allowed to use graphing calculators, but just for the sake of showing what it would look like in a TI-30XA or X2S, this is how I would have put it in. It would go 600 divide, to get your base E exponential, I'll go right where the natural log button is, hit second natural log, then the exponent has to go 2 times natural log again, 125, close that, divide by 6, and we get the figure of 120. So we've got it. The initial size of that bacterial culture was 120, however we looked at it. Any questions at all, folks, seeing it through either Desmos or on a display like this? Okay, another thing to mention, this is going to be not on exam 2. This would be on the 3rd exam, but I'll be making these comments on the 3rd exam. Whenever there is something numerical like this, where we just have to shove something into a calculator and get a value, this is always going to be worth a ton of partial credit. If this was a 5-point problem, I would give this 4.5 points of credit. And even if you made a mistake in the calculator, you would only ever lose a 0.5 point. If I see it correct on the page and you made a mistake, I'll just assume that it was the stress of the exam and you maybe just slipped and hit the wrong key. So if you're in the habit of writing down what goes in the calculator first, that'll be very, very helpful for partial credit on exams. But in either case, we have it, folks. The relative growth rate came out as natural log 125/6. The initial size of the culture is exactly 120. And you could say cells or bacteria, just to mention the units. I'm not picky about units, but it can help out. Well, let's see what else we're getting into. The last thing they ask for is for us to find an expression for the number of bacteria after T hours. This is what they're really saying. That's how we started the problem. We wrote down that expression. P of T is the population size of the bacteria culture. Then we wrote it out in this format. It must be this format. Finally, we're just plugging in what is the initial size and what is the growth rate K. So think of this as filling in the blanks. Now we have a full function. So this is what I would write down for this portion. Population size at time T, that's the number of bacteria after T hours. It's first the initial population size. We'll throw in 120. Then it's going to be our base E exponential to the power of K times T. Well, K's an interesting hefty exponent. I'm just going to put a T right in front of it. It'll look like this. T times the natural log of 125, close the parentheses there, and then divide by 6. So I filled in the green portion and the blue portion. That's all we needed for part C. Kind of strange, huh? Really, part A was the hardest thing, just finding the relative decay, or excuse me, growth rate. Well, any questions, folks, on getting our expression for the bacteria size? Okay, now that we have it, once you have this right here, it'd be not a bad idea to do some check work on this. Let's put it in Desmos. I'm gonna write it as P of T equals 120 e to the power T times, oh, that didn't work. Doesn't want to do it. There we go. Natural log 125 sixths. Okay, so that's our function. Then you could just go and say, if that function's correct, it had better evaluate by telling us population size at time 2 is 600. So let's go P of 2. And yeah, it tells us that is 600. We want to be extremely sure. Let's see if population size 8 is the right figure. It says population size 8 evaluates to 75,000. So it looks like we're in business. But the trouble is, I don't have Desmos on an exam, so I can't do it this way. You could for homework, that's not bad, but in an exam setting, well, we need to actually write this out. So I'll solve it that way. Find the number of cells at 3 hours. Just take your expression above and write population size, input 3 hours will be equal to, come back over here, and the only thing we're changing is the T variable for time. So it'll read in as 120 e to the power of 3 times natural log 125 sixths. So from here, again, you could simplify the function right here to here, or just crank it all out. Let's throw this into a not as intelligent Desmos calculator and see how it goes. So first, go 120 times e to a power 3 times, oh, and that doesn't look good. That's not going to the exponent. Seems to have trouble with exponents on here. Natural log 125, then divide by 6, and this is the figure we'll get. Well, it's awkward because we can't have 0.6407 amounts of bacteria, but it's just a model. It's not meant to tell us the exact number of bacteria, or you could say that maybe some of them are about to divide. We'll round to, yeah, let's just round down to the nearest, or round down to 1341. We could say the next one hadn't completely formed yet. So any sensible rounding that makes sense to you, I'd say go for it and you'll be in great shape. So 1341 cells. I'll put this little wavy thing here to say, now it's just an approximation. It's about what the model's predicting, but we're not expecting an exact value. Other questions or comments so far? Okay, so the number of cells at 3 hours, it's just a function evaluation, but this one is different. It's saying, find the growth rate at 3 hours. Very different question, right? Here, we're not plugging 3 hours inside the population function. That's just the number of bacteria after 3 hours. Exactly. Because it said growth rate, here's what we're using. We go back up here, and yeah, we're using this. It's just going to be K times P at 3, really. Let's put down the whole formula. The growth rate at 3 hours would be exactly rate of change of population size with respect to time. We're going to throw an evaluation bar at 3 hours. And the formula goes K times P. But for evaluating, we can say P at 3 hours. Notice we kind of have half the information right there. We're just taking K, which is up here, natural log 125 sixths, and multiplying it by 1341. So it's on paper. First for K, natural log 125 over 6. Then for P at 3, we already calculated it. It's multiplied by 1341. Now here, I'm going to get a kind of a heavy approximation because I'm using an approximated value. You can either use the 1341, that's completely okay. I'll use this value right here, getting just the extra precision. So my answer might be slightly different. Or
Yeah. like-
you're saying this all right here?
Yeah.
Yeah, all that is really just this, exactly. So what we could do is just keep on multiplying, right? Leave it right there, it's in its exact form, that's the only thing that's missing. So is that what you were mentioning, just throw the extra bit in?
Yeah.
Exactly, that's the best way to do it. In your calculator, you could use the previous value, just multiply it by k. So it's gonna be times natural log 125, divide by 6 again. And this is the figure we're getting. 1079.6, let's put this in. Let me try to put it in a spot where it's gonna fit. 1000, I already forgot, let me try again, 1079.6. Move that out of the way. Cells per hour. So that's what is happening if they ask us for a growth rate. If you hear the word rate, you need to have a mixture of units, something per something else. That's a hint we're dealing with the derivative. But watch how this problem goes. Really, we just took information on part D, combined it with information on part E, and that's the whole way to get through this one. Yeah, go ahead.
Where'd you get the 1341, or you have 1341, but why did you get 1341, and at the end, we multiplied?
Oh, the 1341
Yeah,
came from right here, P of 3.
okay, and so you just added in, you multiplied at the end, oh.
Yeah,
gotcha, that
exactly.
okay.
My color coding would help out if I kept it consistent. The K went in there in blue, and the P of 3 was really just the above step. So we used that prior information, just dropped it in and
Right.
took the K value, carried that down as well.
Okay, so you combine both there, right, that makes sense, cool.
Awesome. Other questions so far? Okay, now the reason part E is kind of a tricky question is it's happened before in exams and I always felt really bad about it, so I always make a big deal out of it. You can solve part E by going right here, calculating its derivative from scratch and then plugging in 3 hours. But it was never meant to be that long of a problem. It was also mainly a problem to know that the derivative is already supplied. Really weird, right? Usually we have a function, we find the derivative. In this problem, we started with the derivative and they told us what the function was. So it's kind of an unusual situation. It's a situation where you'll know your function and your derivative all at once. Well, I think we're just about there, folks. We have one last question on this one, part F. When will the population size reach 100,000? But any other questions at the moment? Yeah, go ahead. I'd be okay with 1341, absolutely. Oh, when I see your number, it's gonna be a little bit different. In fact, let's check it out just to see. If we go 1341 times natural log 125 divide by 6, you know, we're really, really close. We're off by about a half point, less than 0.5 even. So yeah, if you use that value there, I'd be okay with that. Other questions or comments at the moment? Okay, so part D was asking how many cells after a certain amount of time. E is telling us at that time at 3 hours, sure, there's 1,341 cells, but it's growing at a tremendous rate. Eventually that rate must be skyrocketing because at 8 hours, there's already 75,000 cells. But now part F is totally different from all those. They want to know the time, when will a population reach 100,000? It's hard to guess because we know at 8 hours, it's at 75,000. So if I were to guess, I'm thinking like maybe 8.5 hours, something along those lines. Well, the way to start off this one, we have to focus on this right here once again. And we're just going to write population size equals 100,000. So that's our setup on this one. Next thing to do is we make a substitution. On the entire left-hand side, we're going to throw in the 120 e to the power of t times natural log 125 divided by 6. equals 100,000. So that's how we'd start off this problem. Just write down the equation for population size and make a substitution on the left-hand side. Now it's definitely an equation for which you can solve for the time Tn. Now, I guess first thing we have to do is divide by 120. We'll get e to the power t natural log 125 sixths. Then back to our calculator. We want 100,000 divide by 120. It looks like it's repeating. I'll call this 833.3 bar. If you called it just 833.3, that'd be completely fine as well. And when I write this as a real exam question, I'll try to be specific with rounding, so we're not worried about guessing what's appropriate, what's inappropriate. Probably would have just said round to 1 decimal place. Now to this stage, we're going to use our trick, take the natural logarithm of both sides, and you'll cancel the base exponential. So it looks like this. Natural log e to the power of t times natural log 125 sixths equals the natural log of 833.3 repeating. I forgot to put my bar on it. I wanted to put the bar to show repeating on it. We get a cancellation here. And this is a decent shortcut. If you go from here down to this line, t natural log 125 divided by 6 equals natural log 833.3 repeating, I'd say that's a fine shortcut. It would mean you're taking the natural log of both sides. The step in the middle is more for the sake of notes, just to show what really happened in between those steps. Finally, we just need to multiply by 6 over natural log 125. T is then 6 natural log of 833.3 repeating divide by natural log 125. So that's our full value that we'll be using. Any questions, folks, to that stage? Okay, again, if this is on your paper, I tend to essentially give you all the credit, even if we made a mistake in the calculator. But let's give it a try. I have the 833.3 repeating, but I feel like if you're putting this in the calculator, it'd probably look more like this. 6 natural log 833.3. I'll just give it a bunch of 3s until we're satisfied. That's enough of them. Divide by natural log 125. And that's our time in hours. About, let's say we round to the 10th of an hour. In about 8.4 hours, we expect 100,000 bacteria in this culture. So approximately 8.4 hours later. Do those numbers look all right to folks? Awesome. So that's our big rundown on a growth equation like this one. A real problem on a homework is not necessarily going to have all of these parts. This is like 2 questions really rolled into one. And a real exam question has to be directed. They're timed exams, so they'll always go pretty fast. Well, any questions at all, folks, on getting through this one? Okay, well, if we have exponential growth, we must also have exponential decay. And if there's exponential decay, we hope that there's some great formulas. Here's the formulas that are sometimes very, very handy. So whether it's a growth or decay problem, you'll have either doubling time, tripling time, or a half-life, or a third life, or a quarter life. There's a really kind of a cool analogy to this. If you want to find the doubling time formula, you could call it T2, time to double your investment or your population. And T2 just becomes natural log 2 when we go to derive this. If you want a tripling time, you could call it T3. All you change is that. So a quadrupling time, the time for your population to increase 4 times its initial size, is just going to be natural log 4 divided by the relative growth rate. So really friendly problems. But when we start talking about half-life, it feels like it breaks down. There should be a half right there, right? Turns out there really is, because if you look at that formula, there's a couple other ways you could write it. That negative sign you could treat as an exponent, and it becomes natural log of 2 to the power of -1 divide by now the decay rate K. So this is really natural log of 1/2 divided by K. So if we were talking about a half-life, we're going to denote it by lambda. And essentially, this is what happens. Take the natural log of 1/2, divide by K. Somehow, some way, though, people decided this looks simpler as a formula. I kind of agree. There's less fractions. There's not a half inside the logarithm. And they just throw in a negative and you have the correct formula. So this one's more standard. It fits these patterns up here. If we want, say, a quarter life, we would just put natural log of 1/4. Or negative here with a natural log 4 would do the job. But half-life is way more typical. And so here's our next formula. For given this equation, it tells us the half-life is negative natural log 2 divided by K. But oftentimes it's K that you're looking for. So if you solve this for K, you would write K equals negative natural log 2 divided by your half-life lambda. So that's another way to write this out. Both of them are just as fine, but this is sometimes the one you want, the value solved for K. Well, with that in mind, here's a pretty fast problem based off what we did earlier. Any questions so far? Okay, this time we're dealing with strontium-90. I have no idea what that's for. Anyone happen to know a good application of strontium-90? Let's take a look. I mean, this is always good to try to relate to the problem you're working on with something in real life, if it's something from real life. Oh, it's the bad stuff. Nuclear fission. Yeah, that's breaking things apart. So this sounds like bomb making material. Who knows?
There's
Oh.
if you search it up, I'm pretty sure there's a core. There's the core strontium like buried in North Carolina or something like that. In Eureka, North Carolina, put on a big nuclear reactor where we accidentally dropped.
Oh, no.
But let's say the number didn't go off.
Mhm.
We never found strontium, something like that. I don't know, we had a core of nuclear waste sometimes out there.
That's terrible.
Buried somewhere in North Carolina.
Probably in this article somewhere here. Well, I'm not sure on the application, but there's been some massive problems with it. Good news is half-life is 28 days. So, I mean, it still is going to take a while for a massive spill to evaporate. It will become annihilated, but better than 28,000 years, right? So we have a half-life of 28 days. We can start by writing lambda as 28 days. Now on part A, they tell us some other information. A sample has a mass of 50 milligrams initially. Now it says, find a formula for the mass remaining after T days. Well, the moment they told us we have a half-life, that means K is on the table. We have a constant relative decay rate. And you can immediately say mass at time T equals initial mass, M naught, times e to the power of K times T. So that's what we would put together right away, just from having information on half-life. There's an associated formula, we ought to write it down. The rate of change of mass with respect to time is going to be K times mass. If we input a value, say like maybe 70 days or something like that, we would say mass of 70 days. But in differential equations, they typically suppress the input. We just write it out like that. So we have that information so far. They even told us an initial value. When it says 50 milligrams initially, they supplied us with the initial mass, M of 0 is 50 milligrams of strontium-90. So that's lovely. We also need the K value. If they gave you a half-life in a roundabout way, they also gave you the decay rate K. So we can say next, K is equal to negative natural log 2 divided by lambda, the half-life, which we were informed is 28 days. So that immediately goes inside. Then finally, the end answer to all this is, we can say, therefore, the mass remaining after T days is going to be your initial mass of 50 milligrams multiplied by an exponential function that's decaying due to the negative sign we see right here. So it's going to be K times T. I'll sneak the T in between that negative sign. So negative t times natural log 2 divide by 28. It's always kind of weird to write these in. I usually kind of try to write it sideways so you can tell what's the exponent and that the division by 28 is still in the exponent position. So compare that to example 2. It's kind of amazing. If you have an initial value and good information on k, putting the function together is way quick. Took us about 20-ish minutes on our second example to get to this stage. Now all we want to know is how much mass remains after 40 days, but sometimes it's fun to do kind of an experiment. Before you even calculate this out, we knew we had 50 milligrams. I'm going to multiply this by 2 to the power of -1. That's just going to cut it in half. So there's 1 half-life gone by, and we're at 25. Find the mass remaining after 40 days. Let's let 2 half-lives go by. That's going to be 56 days. Not quite the 40 we want. But at 56 days, there's 12.5 milligrams. So I'm expecting just a little bit more than that altogether. So if you can think of those kinds of terms, it helps out because sometimes it's easy for me to mix up a negative sign or the 50 and the 28. If you have an expectation of what should happen, you can catch a lot of simple mistakes like that. Well, let's give it a try then. Mass remaining after 40 days. Let's put in mass at 40 per days. The value 40 is going to go right where t is right here. So it'll be 50 e to the power of -40 times natural log of 2, all divided by 28, still in the exponent spot. Now let's just crank this out. So pick your favorite calculator. I like the TI-30X2S because you can put your information in one long line. You don't have to work inside out, which to me is a lot trickier. So I'll go 50 e to the power of -40 natural log 2 divide by 28. So they're telling us there should be about 18.57. When we did 2 half-lives, we had about 12.5 grams. So I'd say that's in the right ballpark for us. It didn't say what to round it to, so I'd say use your best judgment. About hundreds probably seems about right. So 18.57. In units of milligrams. So finally, that's the conclusion to that one. Any questions, folks, to that stage? Okay. Now part C says, how long does it take the sample to K to a mass of 2 milligrams? But I want to add an extra question to that. I know that sounds kind of rude, but I notice I'm neglecting on example 3. I want to pull this again in just so that we're familiar with dealing with it. So I'm going to write in this extra information in red, just so you know that this was added after the fact. At what rate is a sample decaying at this time? So sorry, part C has 2 questions, but the second portion is really fast. Put that in red just to show that was a edit really quick here. Actually, I probably need the second page to get through this one. I think we have enough time to give this a try. Any questions before we dive into the second one, folks? Okay, so here's how I'd probably start this off. They ask us, how long does it take the sample to decay to a mass of 2 milligrams? Because the question is how long, we go here, that's what we're solving for, that time t. So I'll write mass at time t equals 2 milligrams to start. Then last thing I'll do is copy in this entire portion right here that's temporarily circled and make that the left-hand side in our brand new equation. So it's going to be 50 e to the power of -t divided by natural log of 2. Oh, sorry, I have an extra division in there that shouldn't be. Let me try one more time. -t times natural log of 28, or 2 divided by 28 is equal to 2 milligrams. So finally, we're in business. First thing I'll do is just divide both sides by 50. we'll get e to the power of negative t times natural log of 2 over 28 equals 2/50 or 1/25. Now we can take natural log of both sides. So here's the massively important step. Inverse function goes in, the natural logarithm of e to the power negative t natural log 2 over 28. It's also the natural log of the right hand side, so natural log of 125. Oh, it was 25. Thanks for spotting that. Just was really interested in larger numbers for no apparent reason. Thanks for seeing that, folks. Now we have another cancellation here to here. And it's just a couple steps away. So now it's negative t times natural log 2 over 28 equals natural log of 1 over 25. So I'll be multiplying both sides by negative 28 divided by natural log 2. That solves for t immediately. So t is negative 28 is going to multiply into the numerator. So times natural log of 1/25. And the denominator will be natural log of 2. Yeah, go ahead.
Would you be able to replace the natural log of 1/25 with that negative?
Yeah, absolutely. Right at this step, you could have said it's negative natural log of just 25. I think that's a pretty good step to take because when you look at this number, it just looks wrong, right? We're trying to find a time and it looks like my time is negative. But good eye, if you see a 1/25, that's really a negative number right here. And you can use this kind of work to see it. Or a different approach, if you graph the logarithm function, it looks like this. Here's the value of 1. So 1/25 is going to be way over here, giving us a negative result. Well, either way we do it, we now need to jam this into the calculator and see what the result is going to become. So back to the calculator. It is, for the numerator, negative 28 natural log of 1/25. Almost did that again, fixed it. Then divide by natural log of 2. So it says we need to go about 130 days altogether. Let's call it 130.03 days in order for the 50 milligrams of initial strontium-90 to disintegrate down to just meager 2 milligrams. So it'll take a good part of a year, not too crazy. Well, any questions, folks, to that stage? Yeah, go ahead. Oh, it was from this step right here. I've divided this 2 by the 50 to get to the 1/25 here. Other questions at the moment? Okay, I'm going to, for the sake of the notes, this is mainly a reminder. Circle this and say, my pen is lagging, are here. It's weird when the pen lags. Since I feel like we don't want to rush in 3 minutes and some change that last part that we added in. Does that sound all right to everyone? Okay, so we got through the first part of part C. We found it's going to take 130.03 days. And now the follow-up question that we'll solve next time is, in 130.03 days, there's just 2 milligrams of strontium-90. How fast is it disintegrating then per day? Well, this will be a good stopping point for us then, folks. On Wednesday's class, we'll return here. We'll finish off these notes and be in section 3.9. Well, have a great night. Try to stay dry out there. If you have any questions, I'll be happy to help out.
For
Yeah.
22, what does NKM represent?
Oh, this is newtons per kilometer. So the newtons is the unit of the force function F,
So,
and the kilometer is just the distance between the smaller mass and the larger mass.
so F would equal N, or
Sorry, say again?
would F equal N, or what? I don't
Let's
know,
see.
that's like
Yeah, F is going to be equal to exactly 2.
2.
So if you take your derivative right here,
Oh, I didn't see.
evaluate it when R is 20,000, you're going to put 20,000 here and here, and it's all set equal to 2.
Oh,
Or excuse me, Well, that's
two.
tricky. It's really negative too, because they said decreases.
Yeah, yeah. So it's just gonna be like -2.
Exactly.
Actually, well, since there's already a negative right here, it's just gonna be 2n equals this with the r replaced with 2000,
Exactly, yeah.
and then how would I go calculating that from there? Like,
Well, your goal is really, you're trying to solve for this, the constant G, little m, big M, as
Yeah.
one big thing. Once you solve for that constant, you can go back to the derivative and address
And then-
this question here.
oh, okay.
You'll plug 10,000 inside here and here, the constant you solve for, and you'll have a
And
value.
then replace like the 2n with the f to figure it out.
Yeah, exactly.
Okay, thank you.
Yep, you betcha. Sorry, this is tricky.
So it doesn't have to pertain to math, that's gonna be really quick.
Sure.
So the
Oh,
lambda
okay.
looks almost exactly like the Gemel in Hebrew.
Oh,
And so
interesting,
that-
yeah.
that
What was
must-
that
yes,
called in
so
Hebrew?
It's the Gemel,
Gamel.
it's basically the G.
If you're curious, there's this really cool math symbol that's used, it's an actual Hebrew symbol
Oh,
that's
is
used
it?
as a math symbol. Aleph.
Oh, the olive. Okay.
So that's actually used as a real math symbol.
That's
But lambda,
weird.
I guess it just kind of looks Hebrew-y.
Well, lambda's Greek, so.
Yeah, geographically, that kind of makes sense. That's kind of
Yeah.
cool. Thanks for showing me that.
So, okay, so I'm so sorry, I got.
Oh, no worries.
Okay, so. For this form, are there like multiples of these? Like it's such a weird concept that we have the derivative and then we have our regular formula. Are there more formulas where we would immediately just have the derivative that like how differentiate?
Yeah, we
Like-
are in fact gonna do that again on our notes. For example, when we go to Newton's law of cooling, it starts like this.
Okay, and that's our derivative, yeah.
That's our derivative,
Oh, yeah.
and the solutions are exactly that.
Okay,
Kind of weird because, I mean, we haven't taken differential equations. They haven't shown us the solution method at all to any of these.
they're just like a matching set. So we just trust that taking the derivative of t of t, I guess, gets us, oh, like normal.
Yeah.
Okay, so I
And
guess it's that.
honestly, if you think back to college algebra type content, where did that even come from? Because they never even told us the differential equation. We just had to take on faith value that described all of the growth problems and all of the decay problems.
Yeah, that was actually, that was gonna be my second bit, was I was confused by, so every time, so, sorry, an indicator that we're dealing with a, what is it called? Differential equation problem.
Mhm.
What's kind of like that indicator in your head that makes you think like we can use these types of equations? So we have this. Anything that says exponential function.
Or not necessarily, oh, sorry, I was just clicking randomly.
Oh, sorry.
My bad. No, I would say, sorry, could you rephrase your question?
Yeah, so like when I'm going through like a test or just random like homework. And like if it was all random, all mixed up, how would I
Yeah.
know that this problem, how would I know to solve it this way? Using differential equation.
I would say anytime a question comes up like, say, this, if you're told to find a growth rate, then we can say right here, well, this is itself the growth rate right there.
Okay. How would I know that we have like growth rate, I guess what I'm kind of asking, like, so it's asking to find the growth rate, the
Yeah.
derivative.
Mhm.
How do I know that we already have that? Like,
Oh, yeah, that's just kind of the thing that we'd have to be aware of. Anytime you use this function, this has to come into play.
that's.
And so I would say the best practice is if you're doing like an exam question and you see, say something like this, where something is growing, this is the major buzz line, constant relative growth rate.
Constant relative growth rate. Okay.
I from right there would immediately put this down and this down, both of those equations.
Constant relative growth rate, okay, and then it's always following that template that.
Yeah, exactly. And in the other one we did, it didn't say constant relative growth rate, but what it did say was, I went too far. No, I didn't. Sorry, it said it has a half-life. Half-life is telling us, well, a decay rate instead. So anything that says half-life, you could immediately put down this decay equation and the decay rate right there.
growth and decay, oh my gosh, I'm sorry, so growth and decay equations are all these things.
Exactly, yeah.
Oh,
And
there's
what
just
decides the
family,
differences?
oh, okay.
Yeah, it's just that what K is. If it's positive, you have growth. If it's negative, you have decay.
Thank you, that makes so
You
much
betcha.
sense. Oh my gosh, yeah, okay, I think that's all I have right now, thank you so much.
Gotcha. Yep, you betcha.
Yeah, and seriously, thank you so much for staying after class and answering questions. It's like the first math class that ever happened.